Hello, this is Dr. James Camp, and this is from Lee College in Baytown, Texas, and this is my lecture on neurotransmission, which concludes our discussion of neurophysiology for my class and Dr. Ross's class. We're going to talk about neurotransmitters and synaptic transmission today. Okay, so as we know, we've got an action potential traveling down the neuron, reaching the synaptic knob. We now have a voltage-gated channel of a different kind. These are voltage-gated calcium channels. Okay, so when the action potential reaches the axon terminal or synaptic knob, the signal has to jump across the gap. Somehow the signal has to clear the synaptic gap here. The synaptic cleft. Okay. Occasionally, these two cells will fuse with a gap junction, allowing the electrical signal to pass directly from one to the other. But almost always, we use a different mechanism called neurotransmission. So what happens is voltage-gated calcium channels open, and these calcium ions stick to the walls of the synaptic vesicles, and they cause the synaptic vesicle to merge with the plasma membrane on the synaptic side of the presynaptic side of the axon terminal, and that spills the neurotransmitters that our synaptic vesicle was carrying out into the synaptic cleft, and those neurotransmitters bind to receptors and cause and allow charged ions to travel into the postsynaptic cell. Okay, so what we've got here is that the electrical potential cannot jump from cell to cell, so the neuron has to release neurotransmitter molecules that will bind to receptors on the next cell's membrane. There are essentially 6 steps that take us from an action potential on the upstream or presynaptic neuron to a graded potential on the downstream or postsynaptic neuron. The arrival of the action potential at the synaptic knob opens calcium channels on the synaptic knob. So calcium rushes into the synaptic knob, and that calcium causes synaptic vesicles to release neurotransmitter into the synaptic cleft. The neurotransmitters bind to receptors on the postsynaptic cell membrane, and the receptors on the postsynaptic membrane open usually Na+ or Cl- ion channels, depending whether this is a stimulatory or inhibitory neurotransmitter for this type of cell. So our sodium or chloride ions move into the postsynaptic cell's dendrite or soma. This slightly raises or lowers the membrane potential, causing a graded potential to occur. Here are two examples. In a cholinergic pathway, which is most of the peripheral nervous system, that uses acetylcholine as the neurotransmitter. Whenever you see this ergic terminology, this means that the pathway is energized by a particular neurotransmitter. So look at what comes before the ergic and try to interpret that. So cholinergic, that comes from acetylcholine. Adrenergic comes from adrenaline, which is the old name for epinephrine and norepinephrine. GABAergic is going to be a GABA neurotransmitter, gamma aminobutyric acid, which is the main inhibitory neurotransmitter used in the central nervous system. So the action potential arrives, calcium releases acetylcholine, acetylcholine opens sodium channels, sodium enters the cell, and let's say it shifts the potential from -70 to -60 millivolts. So we're now that much closer to threshold. It won't be quite so high, it'll be more like 65 by the time it diffuses all the way over to the axon hillock, but we're still that much closer to threshold. In the GABAergic pathway, the action potential arrives, calcium releases GABA, GABA opens chloride channels, and chloride enters the cell, shifting the potential from -70 millivolts to -75 millivolts. So we're now moving further away from threshold, so that's an inhibitory example. Finally, I just want to introduce a few neurotransmitters. Some of them you've already met. Acetylcholine is the main PNS neurotransmitter, and you met that in the skeletal muscle chapter because acetylcholine is what excites skeletal muscle. However, it inhibits cardiac muscle, causing your heartbeat to slow down. Norepinephrine is the neurotransmitter used by the sympathetic or fight or flight nervous system, which we'll discuss in a future lecture. Norepinephrine has excitatory effects on some things. For example, it speeds up your heart rate. It has inhibitory effects on other things. For example, it dilates the smooth muscle in your bronchi so that they will dilate. It inhibits the smooth muscle in your bronchi so that they will dilate and let you breathe more easily. If you think about what you need in a situation where you might be fighting or flighting, that is like running from a bear in the woods or something, norepinephrine pretty much produces the logical effect for that. So it slows down your digestion a little bit, but it speeds up your heart rate and makes your breathing more effective and things like that. GABA is the main inhibitory neurotransmitter of the brain. So if you have one of those cases where your brain is maybe trying to suppress a reflex so that you can grab a hot pot off the stove, your brain would be secreting lots of GABA into your spinal cord to try to inhibit that reflex. Histamine influences sleep and memory, or rather it influences awakeness and memory. Histamine is one of the major neurotransmitters that your brain uses to wake you up in the morning and keep you awake and alert and aroused during the day. That's aroused in a focused and paying attention way, not in like a sexual way. Oddly enough, acetylcholine is the neurotransmitter that gets you aroused in a sexual way. So histamine influences your sleep and your memory. That's why antihistamine drugs often make you a little drowsy, is that they keep your body from having as much active histamine keeping you awake. Serotonin influences sleep. Serotonin helps you get to sleep, which is why its precursor, tryptophan, is found in turkey. And that's why a lot of people feel very sleepy after Thanksgiving dinner. Serotonin also helps regulate your appetite, has a major role in learning and memory, and it's most famous for its role in mood. It helps you, it's a kind of mood stabilizing, happiness inducing almost kind of, or at least well-being inducing neurotransmitter. So it's used in pathways that suppress anxiety, prevent depression, kind of keep your mood in a let's go along happily kind of way. It's not a, doesn't induce euphoria, but it keeps you in a good mood mostly. So serotonin uptake inhibitors, SSRIs, prevent serotonin from being taken out of the neurotransmitter. So we didn't mention this, so I probably should. When you have your neurotransmitters in the synaptic cleft here, they're going to stay active as long as they're there. They're going to keep triggering graded potentials on the postsynaptic cell. So at some point, these neurotransmitters get taken back up into the cell that released them, and that's called reuptake. So a serotonin reuptake inhibitor would allow serotonin to be present on the postsynaptic cell, or generating feelings of well-being on the postsynaptic cell for longer, which would generally work against anxiety disorders, work against depression disorders, even helps with people who have certain kinds of post-traumatic stress and things like that. Works for OCD, helps people stop ruminating on repeated things or obsessing and compulsing about things. Unfortunately, it can also excite feelings of mania in people who are bipolar. So you have to be careful with your SSRIs because they can push somebody too far in the feeling good direction. Dopamine is often referred to as the pleasure neurotransmitter or the reward neurotransmitter of our brain, because in basic learning activities, like if you're trying to learn to ride a bike or something and you finally get it right, you'll get a dose of dopamine into your brain that says, remember that, remember how you did that, do it again, do it that way again. That's what gives you that kind of feeling of euphoria when you finally learn to do something and you get it right and your brain just rewards you with that shot of dopamine. Unfortunately, you also get that dopamine from bad habits and addictions. Okay, not just good habits, but the bad ones as well. And a lot of the things that we can attribute, that we can link to the bad habits of modern society, like eating too much, eating too many desserts, or having a lot of ice cream or chocolate, or
racket magic packs,
or buying new things, or going gambling. All of those things are designed to give you a shot of dopamine that makes you feel good about what you just did, and that makes it very hard to break those bad habits. The only real proven way to break a bad habit like that is to link it to something that's at least as good, So I'm going to diet, but I'm going to link that to doing something else that gives me a little boost of dopamine. Like, every day that I meet my diet goal, I can, if you're my son, you can buy a new pack of magic cards or something. So anyway, that's dopamine. Dopamine also has a major influence on your mood. It's been linked to attention deficit disorder. May have something to do with dopamine in your brain. Also has to do with the norepinephrine in your brain and the histamine in your brain and all those things that focus your attention. But it also has to do with dopamine, that people with ADD often crave little stimuli constantly throughout the day that give them a little bit of dopamine to keep them going along. We're inveterate, snackers and shiny rabbit chasers and things like that. Anything that gives you just a little bit of momentary satisfaction. Okay, so that pretty much sums up what you need to know about neurotransmitters. There's much more information on them out there, and I encourage you to keep reading and keep learning. As always, happy studying, and I'll see you in the next video.